So 0.035 squared times by 0.16 times by 0.5 is equal to 98 times 10 to the power minus 6 minus, okay, 0.16 times 0.08 y squared. Okay, so this I will call my equation number 1. So finding the first moment of area is usually the most tricky stuff. Okay, so from here, shear xy as a function of y. So we know that the y the shear stress is shear force is constant, 90 times 10 to the power 3. The Q is 98 times 10 to the power minus 6 minus by 0.08 y squared. Okay. Then you have the second moment of area, which is 5.8133 times 10 to the power minus 6. And then our thickness is 0.16. Okay. That is why we set that limit. The limit is from 0.015 meters to 0.035 meters where y is. Okay. Why that limit? Because of our constant thickness. Okay. Because of constant thickness. So from here, we write out our value. So this is 90 power 3 divided by 5.8133 power minus 6 divided by 0.16 times 198 power minus 6 is equal to 9.483 times 10 to the power 6 minus by 7.741 times 10 to the power 9, and this is y squared. Okay, so that is our equation. So this equation is only for the what? Flange. Okay, I hope it's clearer today. I realized last Tuesday was towards the end, was a big rush. Okay, you guys might not get the important point. Any question from here? Anyone? Are you okay? Anyone? Any questions up to here?
Can you re-explain the depth?
Re-explain which one?
The depth.
The
D.
D?
Yeah.
D is the depth.
But
The
why?
depth of the structure. Because Y is your variable. So that is your depth to the blue line.
Okay.
Remember rule number 3. Analysis starts from the furthest away from the centroid. So that is why this over here, furthest away from the centroid, this is the analysis direction.
Oh, I get it. Yeah.
Okay, that's why the D is that dimension over there. Okay.
Thank you.
Okay. So then the next one we're going to do is we're going to have a thickness. Okay. So the next one is we're going to have the thickness, right? The thickness is equal to twice of 0.02, which is equal to 0.04 meters. And why that thickness now? Okay. Now we are going to our slider or our variable now will work from 0 y and it goes up to 0.015 meters. Okay, and why is that? Okay, so we know the distance from here to here now. This we know is 15 millimeters. So the next set of equation that we're going to do, okay, the variable, okay, or the slider will be in the web section. Okay, so I put down here web section. Okay, so i.e., right, this is where our y will stop. Right, that's why y will stop. However, the first moment of area that we're going to take, you have to consider, right? Now, if we look at the first moment, what first moment of area we're going to take? We have to take this cross-section area. Okay, we have to take this cross-section area. And also consider this area now. I'll use a different color. And we also have to consider the area that I'm coloring in orange. Now, our limits now, okay, our limits now, so this is 0, right? And it will go up to 15 millimeters. Okay. So what I'm trying to say down here, the Q of the flange is now constant. Because the variable y cannot go above 15 millimeters. Okay. It can go to 0 to 15, but it cannot go more than that. So that is why now the limits is set from 0y to 0.015. As I did mention before, the shearing stress is really easy. The complication comes in determining the first moment of area. So now the first moment of area now, right, based on the understanding that the analysis direction starts from y max, yes or no? It starts from the furthest distance away from centroid. So now you write this out. So now you write Q Z as a function of y. Okay, QZ, sorry, there's no comma. QZ as a function of y. So now is QZ of the flange plus by QZ of the web as the function of y. Okay, because this value over here is going to be a what? Constant, regardless of the value of y, where y range from 0 to 0.015 meters. Okay, so now we write this out now. Okay, so again, I write down the general formula for Q is equal to width depth y bar. Always follow this. Okay, so over here, the flange, so the width, so it's a constant number. Now the width is 0.16. The depth is 0.02. The y bar now, okay, the y bar now is 0.035, right? 0.035 minus by 0.02 divided by 2. Okay, so that is the constant first moment of area for the flange. Okay, then now we have to plus. Okay, let me shift this across. I need space. Then plus twice, because you have left web. So this is the left web. And this is the right web. Okay. Okay, so you have twice. So the width is 0.02. Now the depth is 0.015 minus y, and the y bar is 0.015 plus by y multiplied by half. Okay, you can see the trend repeats, right? You just need to know your limits. You can see this trend, right? 0.035 plus y multiplied by 0.5. So the upper limit plus y multiplied by 0.5. Okay. And then from here, this will be equal to 0.035. So it's 80 times 10 to the power minus 6 plus 450. Wait, 0.02 is 4.5 times 10 to the power minus 6. Let me do it again. Yep, 4.5. And then minus by 0.02 y squared. So ultimately, this will be 84.5 times 10 to the power minus 6 minus by 0.02 y squared. Okay. Then from here, we can determine our one. We can determine our equation. Okay, our shear stress distribution equation. So the shear stress, okay, shear xy as a function of y is equal to V, which is equal to 90 times 10 to the power 3 U divided by the second moment of area, and then multiply by the thickness, which is twice multiplied by 0.02, twice because you have left and right web. So this will be equal to 90 power 3, 5 point. So it's equal to 32 point, I got a weird number. Wait, 80 power minus 6 plus. It's correct, 84.5, correct. $32.705 times 10 to the power 6 minus 7.741 times 10 to the power 9 y squared. Okay, let me do it again. Yep. Okay. So this is the distribution from 0 y to 0.05. Now, what if we want to look at below the centroid. Okay, let's say now we want to look below the centroid, and I will specify where is below the centroid. Okay, so below the centroid. Okay, so let me sketch out our line. Okay, so this is above the centroid, and this is below the centroid. So what if we want to find what is the distribution or below the centroid? What's the equation? Okay, so now we know that this distance is equal to 35 millimeters, and this distance over here is equal to 65 millimeters. Okay, so now let's look at shear stress distribution.